Well, hi everyone, this is Bob the Science Guy, and welcome to the channel. We have some exciting news from Shamrock Banks Observatory. I have installed a homemade radio telescope, and I'm live streaming the results to the channel 24/7, at least when it works. Now, a lot of people have seen this live stream, and they seem to enjoy it, but a lot of people are asking, what exactly are we looking at, and how do we read this? So I thought I would take a few minutes and kind of go over the display and show you some of the features that we pick up with a radio telescope, so when you watch it, you have an idea of what you're looking at. So let's get started. Well, I think one of the first things that we ought to have a look at is what exactly is this radio telescope installation? It's something called RadioJove, which is a citizen science initiative started by NASA and taken over by a few dedicated professors, and it's designed to detect radio bursts from Jupiter and the Sun, and to teach people a little bit about radio astronomy. Now, as you can see, here is the website. It's radiojove.gsfc.nasa.gov. And as you can tell, there's a number of training modules that you can look through, and it'll tell you a little bit about how RadioJove is set up and what it does. Unfortunately, a lot of these videos don't seem to work, but the PDF files are intact. Now, before we go too much further, let's ask ourselves a basic question. Why radio astronomy? Well, radio astronomy is kind of neat because radio waves, like any light, is just electromagnetic radiation. And as a result, we can make telescopes that look at radio light just as we make telescopes that look at visible or infrared light. Now, one of the benefits of having a radio telescope is that they're not that difficult or expensive to build, and they don't rely on clear skies. I live in Michigan, and I have an optical observatory. Unfortunately, there are many nights of the year that it's cloudy out and I just simply can't see anything. But with a radio telescope, I can do something every day. Now, like an optical telescope, we have to kind of deal with blocked images. So we look for windows. With an optical telescope, we look for windows between cloudy nights, when the nights are nice and clear. Now, with radio telescopes, we look for a part of the radio spectrum that isn't too active. So if you look at the radio spectrum, these are the U.S. amateur bands, or the ham radio bands here in the United States. Now, an extremely common band for communications is 20 meters. That's about 14 megahertz. And if you look a little lower, you'll see that there are 10, 12, and 15 meter bands in the amateur range as well. Now, another thing that we have to look at is what do these radio waves do when they interact with the ionosphere of the Earth's atmosphere? Now, the ionosphere consists of several different layers. There's a D layer, an E layer, and an F layer. And during the day, the F layer splits into F1 and F2, and they go up to about 200 miles above the surface. Now, depending on the frequency, radio waves will reflect off of these bands of the ionosphere. So we have to choose something that gets good penetration from directly above during the night and the day. Now, with the sun, obviously, it's above the horizon during the day. Jupiter can be above the horizon at the same time the sun is, or it can be above the horizon at night. So depending on the time of year, our main target will vary. Now, the thing that I want to draw your attention to is that if you look at between, say, the 10 and the 20 meter band, that's a really good window for me to be able to look through the sky and see things from outside the atmosphere. Now, this is the RadioJove installation at Shamrock Banks Observatory. In the lower right, you see the observatory dome where the optical telescope is held, and then you see my wife's garden trellis. And on top of that, I have bolted some PVC pipe, and I'm running two 15-meter antennas. These are dipole antennas, and they're arranged east and west. The one nearest us is the south antenna, and the farthest one by the river is the north antenna. Now, those dipole antennas are attached to a software-defined radio using coax cable. I'm using quad shield coax, and these are some of the tools that you use to put the connectors on the end to build those cables. The cables from each of the two antennas should be the same length, generally half a wavelength or a wavelength long. However, there's an interesting problem that you have, and that is that if both the antennas have the same length of cable, they basically look straight up. Jupiter and the Sun are to the south of me along the meridian. And as a result of that, I have to put in something called a phasing cable in the south antenna. And that's an extra 9 feet of cable to delay the signal a little bit from that antenna, so that instead of pointing straight up, it's actually pointing out at an angle. Then we use some software called SDR Console and some linking software, and then a program called Radio Sky Spectrograph in order to get some signal on a waterfall that we can visualize. So let's take a moment and go over my RadioJove display. And then I'm going to show you the official RadioJove website, and I will then talk about some of the differences between his display and mine, and why you should use one versus the other. Now, starting off on the left side of the display, you'll see the time in UTC. This is Greenwich time. Right above it, you're going to see the position of the sun in yellow and Jupiter in brown. Now, this is from my location. As you can see, the sun is still well above the horizon, about 30-35 degrees, but Jupiter is only about 10 degrees above the horizon. And finally, right above, you're going to see the position of Jupiter in relationship to its moon Io. Now, without getting into too many details, let me just say that the radio emissions that we get from Jupiter occur during a very specific geometry of the Earth and Jupiter and its moon Io. In other words, if Io is between the Earth and Jupiter, we get radio signals. And if it's perpendicular or at a right angle to Jupiter from Earth, on either side, we get signals. And these are called Io A, B, and C. Now, there are other signals that will come through as well, but if you really want to see signals from Jupiter on this display, you want to get a time when Jupiter is actually in the Io A, B, or C position. Now, the redder this is, or the brighter it is, the more probability you have of getting a radio signal from Jupiter. Let's go over to the main display and see what we see there. Now, the main waterfall monitors the bands between about 20 meters and about 10 meters. And you'll see a variety of signals in here. The first thing that just jumps right out at you is this big diagonal signal. And these are actually quite common. They occur every couple of minutes. These are ionospheric radars called ionozones. And what they do is there are special radars down at Eglin Air Force Base in Florida that look straight up and measure how high the ionosphere is, whether or not it's split, and if so, what are the different layers of the ionosphere that are visible, and how is radio propagation. Now, you can see an ionozone in the bottom display, which is 10 times longer than the top display. So this is about 2 minutes long, and this is about the last 20 minutes. You'll see that there are several examples of ionozones, and they go to different frequencies. But notice that they start low and then work their way high with time. Now, while the ionozones don't really tell me a lot other than how the ionosphere happens to be propagating at any particular minute, they are useful for tuning RadioJove. You want to have them clearly visible from the bottom of the band all the way up to the top. You want them kind of bright with kind of a reddish or a brown center. That means that you've got enough gain in and you're picking up good signals. And if you look here carefully, you can see a number of them. So for example, here's the big one that we looked at. There's a double one right here, but in between there's also a very faint one over here, and then of course another bright one here. Now, another thing that you will pick up is that there's a lot of horizontal lines, both long ones that go the entire length of the display and short little ones that look like dots and dashes in Morse code. These are local terrestrial radio sources. As I said, down at the bottom is the 20-meter ham range. Up at the top is the 10-meter ham range. That area that looks like it's got kind of a brighter green background, right around 20.1 megahertz, that's the area of the 15-meter band range, and that's what my antennas are tuned to. So I'm just getting a little more background noise from that area because that's specifically what the antennas are designed to pick up. So on the right side, you can see the band in megahertz, and then you see the waterfall, and it moves from right to left. The most recent trace is on the right side, and as you see, we're picking up an ionozone, which we call sweepers, those diagonal lines from the radar at Eglin Air Force Base. And again, that shows you that the tracing has some good sensitivity. Now, we saw the little dots and dashes of local radio broadcasts. You also see some longer broadcasts that are on the ham frequencies where people are having conversations. Now, another thing that you will notice is some vertical lines, and they're of varying heights. And they've got kind of like a light blue or even a greenish background to them. These are basically electric discharges from equipment in the area, from lightning at distant storms. And it's kind of interesting to just kind of watch the display go by and listen to the music. So let me give you an interesting technique that you can use on my installation of RadioJove that you can't use on the official RadioJove. And that is that you can identify events that occurred up to 20 minutes ago and then just scroll right back and see what they were. So let me give you an example. So right here we see what look like a couple of ionozones, or these sweepers. By manipulating the stream a little bit, I can scroll forward or back, and I can have a look at that object or that event and see what it was. So that's kind of a cool feature. Now, speaking of the official RadioJove stream, let's go ahead and have a quick look at it. As you can tell, right here it says RadioJove project, and it's run by Larry down in Georgia. And his channel name is K4LED. And he live streams this thing 24/7 and has for years. One of the things that's a little different about his stream compared to mine is that he has a much more robust antenna than I do. I have 2 dipole antennas. He's got 4 of them forming a square. And they're also what's called folded dipoles as opposed to single dipoles like I have on my installation. And as a result, he picks up a lot more detail. But he also gets a lot more interference. This is not a normal stream for him. Normally his is much cleaner than this. But if you look very carefully behind those vertical bars, you'll see there's an awful lot of detail. And then you can compare that to mine. Mine doesn't have quite as much detail in it, but I think it's kind of a cleaner stream. The other thing is the audio that's with this. I play some soft elevator music with mine because basically I look at it as Lofi Girl for nerds. Larry is doing a more scientific study with RadioJove, and as a result, what he plays in his audio is the static that the radio is hearing, because a lot of these events that you see on the screen, you can actually hear. And that static gives a little extra information. The other thing is his display is calibrated with a calibrator. I have not been able to do that. They were kind enough to send me a calibrator, but I can't seem to get it to work right. So mine is calibrated by a Mark I eyeball. And I've got a pretty good stream here, but I can't really say anything other than relative intensities, whereas Larry can actually measure antenna temperatures and things like that. It's more useful scientifically. However, this is a great introduction to radio astronomy for the average layperson, and that's kind of what I'm going for here. That's the effect that I'm going for. And as you can tell, we have another sweeper, or an ionozone, going by right now. And you can tell that my display is pretty good because I've got a full range deflection of that ionozone. It goes all the way from the bottom, and then it comes all the way up to the top. So my tuning is pretty good on this right now. Well, here we go, the best laid plans of mice and men. I went ahead and got a video of a solar event to show you, and as I was queuing it up, we had a solar event. Let's have a look at it. So, you see the ionozones here, but these large tongues are solar events. And as you can tell, they start high and then they kind of come down at a slope. And this very steep slope that you see here is what's called a type 3 solar event, which is pretty common. Now, if you look down at the bottom, you can kind of see that slope a little bit better. So we've got, these are the 2 solar events right here. And if you look carefully, this is a very sharp type 3 solar event. This one here is a little broader. Now, I am getting a little bit of banding in it, and that has to do with my tuning. But we'll go ahead and fix that a little bit after the broadcast today. But that's what a solar event will look like on RadioJove. And here it is in the 2-minute stream live. And here's what it looks like in the 20-minute stream. Now, if you want, say you pop in and you somehow miss this, And what you can do is you can actually go to the live stream and you can scroll back a little bit until that is in the frame. And you can see what it is. So that's pretty cool. The kind of striping that you see in that is as a result of my tuning. My tuning needs to be adjusted a little bit. Let me show you one that I got the other day when the tuning was a little bit better so that you see what they typically look like. So what we'll do is we'll go ahead and back this up a little bit. You see the real time on top, then you see that kind of striping on the bottom and the time lapse. But that's a little bit more what they look like. Notice that they're slanted a little bit, starting off at the top and then working its way down. And again, if you miss it, you can pretty easily identify it down here on the bottom screen and scroll right back to where it was and then just kind of let it go by and get a good look at it. So that's a pretty good introduction to RadioJove. We talked about what the display looks like. We talked about some of the things that we're looking for, specifically the solar radio bursts. Now, solar radio bursts come in several different types. There are 5 basic types. The ones that we're going to see are type 3, which are thin and rapidly descend from high frequency to low frequency. They've got that really steep slope. Sometimes you will actually see kind of an aftershock from those bright descending tongues of yellow. Where it's a little bit fainter, but it kind of lingers a little bit. That's a type 4 radio burst, and it's kind of an aftershock of a type 3. Type 2 radio bursts are also associated with flares. The type 3s occur when the flare magnetic loop breaks, and then as it collapses and a shock wave is formed, that becomes a type 2 radio burst. They tend to also be sloped downward, but at a much narrower angle. They're kind of a little broader, and sometimes you may actually see a harmonic at twice the frequency. Because of the frequencies we're monitoring, we're not going to see that harmonic very often. But once again, the type 3s are sharp and down, and the type 2s are kind of broader and a little shallower. So if you have a few minutes and you're interested in just kind of listening to Lofi Girl for Nerds, go ahead and tune in my RadioJove live stream. It's also a lot of fun to compare my stream to the official RadioJove stream at K4LED. So until then, clear skies, and I'll talk about Jupiter radio emissions when we get a few nice ones. I think that will probably be best maybe in a couple of months when Jupiter's up at night, because right now Jupiter and the Sun, as you can see, are pretty much co-located. They're right next to each other. And the Sun's radio bursts are much stronger than those from Jupiter, and they tend to wash each other out, although I have picked up a few of them. If I see some more, I'll let you all know, and we'll have a look at them. Take care, guys.